So the next thing that we're going to look at, this is the final lecture in chapter 2, are biochemical reactions. So the first example will be spontaneous conversion from A to B. Then we're going to look at spontaneous complex formation. And finally we're going to look at the conversion of a substrate into a product catalyzed by an enzyme. So that's non-spontaneous. Because it is enzyme catalyzed. Without the enzyme you will not have the conversion. And so this is spontaneous. Complex formation. And this is spontaneous conversion. And this is also, of course, a conversion. Okay. So, let's start with the spontaneous conversion. So, due to the reaction, the number of molecules, the number of A molecules decreases and B number increases. Right? So since the conversion is only from A to B, we will gain B molecules and we'll lose A molecules. Now, if this reaction occurs in a fixed volume, then the concentration of A goes down and that B goes up. Okay? Why is that? Well, the concentration of A equals the number of molecules of A that I have divided by the volume. And if I have a certain volume V with a certain number of A molecules, then the concentration is that number of molecules divided by that volume. Over time I lose A molecules because B molecules are made. So the starting amount of A molecules, so at time 0 when I start, let's say I have 10 A molecules and no B molecules. So Na plus Nb equals 10. I know that over time this number will always equal 10, because whenever I lose an A molecule I gain a B molecule, so I continuously keep the total number of molecules regardless of their identity equal to 10. Okay, so that's one thing we realize now. The total number of molecules equals the total number that you start with. So we can improve this equation. We can say, look, at any time, for the total number of molecules that I have at any time equals the total number of molecules that I started with. Okay. So that must mean that if the concentration of A goes down, that B goes up. In fact, I know if I lose one molecule of A, I gain one of B. So the change in the concentration of A is going to be equal to the change in the concentration of B. Always. So when I look at the slope of these curves, so going like this, right? Start at 0. Eventually you have no A anymore, then B can no longer be made. You know that the change in A at every moment in time is going to be equal to the change in B. Okay. Now, typically we write this change as a slope. At the change in A and B per unit time is always going to be equal. One rises, the other one increases. So there's a minus. So if this guy goes down, it's minus, the other one is positive. Okay, so we know that too. And because of this, this is true. So what holds for the concentrations, of course, also holds for the numbers of molecules when the volume is fixed. Because this is preserved when you would divide this by the volume. It doesn't matter. Because if they're equal and I divide both sides by the same number, they remain equal. Okay? So any loss of a molecule, of one molecule of A, is accompanied by a gain of one molecule of B. That's what this says. So the rate of change, so the rate of change is in the concentration of A, this thing, equals minus the rate of change in the concentration of B. Any loss in A is accompanied by an equal loss in B, in terms of the number and in terms of the concentrations. Now we need to know the next step is the following. So what we don't know is that we realize now, okay, that the change in the concentration of A is going to be equal to the concentration of B, taking care of minus. But how is this change? How are these changes related to the number of molecules of A? Okay, so if you think about it, if you have more molecules of A, at that moment in time, more molecules of B are being formed than when you have less molecules of A. So, because all these conversions of A into B occur independently, a system with 3 molecules of A has less conversions per unit time than one that has, 9? 10. Right? 10 molecules of A, 3 molecules of A. Here you have more conversions from A to B than that. In fact, if I would have 6, well, let's say 5 here, and I have twice the number of conversions of B to B here than when you compare it to this. So the number of conversions of A to B logically is, it's going to be proportional to the number of A molecules that you have, right? Because they're all independently falling apart. So when you have more of them, then per unit time, more will fall apart. If you have twice that number, twice as many fall apart per unit time. So the concentration reduction in A is going to be proportional in A and a constant. Now since we're losing A, it's going to be minus a constant. And this constant tells you how stable A is. If K is low, then A molecules don't quickly fall apart into B or convert into B. If K is large, then this happens very often. So this is a rate constant, a property of A. If A is stable, K is small. If A is unstable, K is large. Okay, so that is the description, the mathematical description of this reaction. If you would do a measurement, you would measure the concentration of A and the concentration of B. You would find a time after which everything is converted and there is a decay in A. In fact, if you solve this differential equation, you will see that the concentration of A at time t equals the concentration of A at time 0 at E minus KT. Okay? So if you integrate this guy, this differential equation, you get this result, which is this. It goes down to 0. Okay? So that's something that we should realize. That you can write down these rate descriptions in terms of rates of reactions. Okay? So we can write down ordinary differential equations that give the slope of these curves. And we can link those to the rate of a reaction, because this is the rate with which A is converted into B. And that is the reaction, so this is the rate of the reaction. Reaction rate. Now consider this case. So now we know, now we're asking, okay, CA, we're losing A, of course at the same rate as we're losing B, because in one complex of A, B, you have one molecule of A and one molecule of B. And this is going to be equal to the rise, so that loss term is going to be equal to minus the rise in the concentration of AB. Okay, so it would have been this, and it could have been that. Or it would have been 3. It would have been 3. Because you lose B at 3 times the rate of A. So if I give you €1, I gave you 4 quarters. So the rate of euros equals 1/4 of the rate of quarters. Okay? So that's, I think, intuitive, as long as you, you really think strictly about what you see. One molecule of A, one molecule of B gives AB. When I make one molecule of AB at a certain rate, the loss rates of A and B are going to be the same as the gain rate in AB. And again, this is going to be equal to a constant times the concentration of C and B. And that is not unlogical, because if you think about it, is that if there clearly if there is no A or no B, you cannot make the complex. If there is more A and there is more B, A and B molecules find each other quicker, they collide more often, so that you make more. And the constant K will be somehow related to this collision time equation that we've looked at earlier. 4P dE plus dV. Because this is the reaction rate constant, and that is going to depend on the collision time, of course. If the collision time is short, then K will be high. So K will be probably depend on some constant divided by tau collision. Okay. So if the molecules move quicker, or if they're smaller, the K is bigger. And the rate of complex formation is going to depend, so that is the rate of complex formation is this product. And that's going to depend on K, which depends on A and B, the collision time and the intermolecular reaction time. But also on the numbers of A and B. If you have more, then per unit time, more A and B is formed. I think that's all logical, right? I think that is not a big difference. And those K's are not the same, so let's number them. They are not, of course, not the same K in terms of value. And they also have a different interpretation. Now here the situation is very different. Because S first needs to find the enzyme, and then it can form an enzyme substrate complex. And then E, the product can be formed, right? And maybe even S can fall off before the product is being formed. So first of all, what we notice if you look at this equation is that E is a catalyst, because you start with E and you keep E, you regenerate E at the end, so that means it's a catalyst. So the enzyme catalyzes the reaction. So one way to think about this is that there is an S molecule that fits into the catalytic side of the enzyme. Then it's bound, or it falls off. And then P is made, right? And the enzyme is preserved all the time as a catalyst, as a surface on which the reaction takes place. So the rate of this reaction, so we would denote that by V, okay? So, and let's say that is going to be equal to the increase in V. Okay, so the rate of the reaction, of course, is going to, you can quantify the rate of the reaction by the increase in the concentration of P molecules. And that is going to be equal to the loss of S molecules. Because one S gives one P. So the rate of the reaction can either be observed by looking at the concentration of S, which is going down, or by the gain of P. It's going to be the same rate except for the minus term. Now, this rate is going to be proportional to the number of enzymes, because if you have twice the number of enzymes, then you have twice the number of reactions per unit time, right? So the enzyme concentration, the enzyme concentration is going to matter. And how active the enzymes is. So there will also be a K, there will also be some K constant associated, and that's a property of the enzyme. And that's its conversion rate that it has per S and P. But it of course also going to depend on the concentration of S and the concentration of P. You need both, right? And I guess many people would think, now we're finished, considering the analogy with the previous part. That is not true. It turns out to be more complicated. It turns out it was not a product with P, of course, only S, because S was the substrate. It turns out that you get something like this in the end. So it turns out that it is not only the product of the enzyme concentration and the substrate concentration that matters, but in addition there is this other term. There is an affinity term that plays a role. And this affinity term, so this Ks, which is sometimes called an affinity constant, of course has to do with this part, with the binding and unbinding. Because if the unbinding is a lot more probable than the binding that the enzyme has a low affinity, so the enzyme is not very sticky if S tends to fall off rather than be converted. So that the affinity is low. The affinity is high if every S that binds is converted into P. So we need a sort of a stickiness constant, right? In addition to what happens, in addition to the rate of the reaction, which is this part. And that is determined by the enzyme complex determines this rate of the part of the reaction, whereas the binding and the unbinding has to do with the affinity. So that is why this model is fundamentally different from this one, because we regenerate the enzyme. And you can bind to it and you can dissociate from it. And how these type of equations are derived is part of enzyme kinetics, and that is not really part of this course. So that's going to be another course called basic modeling. The next one if you choose system biology. Okay, so we have spontaneous conversion. We have the spontaneous complex formation, and we have enzyme catalyzed conversion. So these are basically the key biochemical reactions, the key classes of biochemical reactions that occur in networks. And each of them leads to changes in concentrations of the reactant. So A is a substrate and B is a product, and they're both a reactant, substrate, product, reactants, substrate, product, reactants. And in addition we have an enzyme as a catalyst. And in all cases the reaction leads to changes in concentrations of substrate and products. And these changes of substrate and products can be associated with rates of reactions. These are all rates of reactions. And their mathematical description are rate equations. So this is a rate equation, a rate equation, a rate equation. And we need to know these rate equations. You can deduce them from data, and if you know them, you can predict what the outcome of experiments are. If we will know these rate equations for all the processes inside the cell, then we could in principle model the functioning of the molecular network inside the cell. And that's one of the one methodology in system biology is to make these models. Okay, so this closes chapter 2. We really came from a static molecular biological point of view on cells to a kinetic dynamic description of the molecular networks that underlie cell behaviors. They underlie self-maintenance, self-repair, self-adaptation and self-fabrication. That's it.